My name is Nick Spinale, and I'm part of ARM research in Cambridge, UK. This presentation is about how seL4 could leverage the ARM v8 security extensions, also known as TrustZone. This work has grown out of a project within ARM research that lies at the intersection of confidential computing and virtualization. Confidential computing is a broad area of study encompassing a range of cryptographic, hardware, and software approaches to protecting data in use, that is, as opposed to data at rest or in transit. Let's focus on a cross-section of confidential computing concerned with the protection of familiar workloads from the operator and environment of the hardware they run on. Consider the relationship between a cloud provider such as AWS and a customer. A customer may not trust the cloud provider with their data. Even if a customer trusts the intentions of the cloud provider, there's still the threat of co-located virtual machines of other customers exploiting vulnerabilities in the cloud provider's platform to mount cross-virtual machine attacks. Further, the cloud provider itself may not want access to the customer's virtual machine in order to avoid liability for whatever they're up to. In any case, this customer requires confidentiality and integrity guarantees for their virtual machines that aren't provided by typical cloud virtualization platforms. Similar security requirements exist for mobile platforms. A mobile device is a wild, lawless territory cohabited by apps ranging from your bank to TikTok. A banking application may require a confidential computing environment in order to protect the device's owner from their other applications. Also, there's the issue of DRM, where an app seeks to protect its digital property from the user. A confidential computing solution of the sort we're after requires a combination of hardware and software. Hardware efforts useful for this purpose include Intel SGX, AMD SEV, Keystone, and ARM TrustZone. Intel SGX allows for applications to contain so-called enclaves, which are execution components which are protected from the operating system. AMD SEV enables a hypervisor to create shielded virtual machines whose state and data are protected from a blind hypervisor using memory encryption. But before we get caught up in special hardware features, let's focus on software. In general, we prefer for complexity to live in software rather than hardware, as software is easy to audit, verify, and update. We'll go as far as we can with software alone in order to understand the minimal additional hardware primitives necessary for us to achieve the security we're after. So, how far can we get from software alone? A trustworthy, attestable hypervisor is a good place to start. Our goal will be to deprivilege the host operating system so that guests will only need to trust the hypervisor and not the host operating system. In other words, we're after a virtualization platform with a minimal, attestable, trusted computing base. This diagram outlines how a typical virtualization platform is structured. The privileged part of the hypervisor effectively includes the host operating system. In KVM, the host operating system is itself the hypervisor. In Xen, the host runs as a distinguished, privileged virtual machine called domain 0. In either case, the host operating system has privilege over guests. We're interested in designs which deprivilege the host operating system. That way, the host isn't trusted with the confidentiality and integrity of guests. In other words, the host isn't part of the platform's trusted computing base. IceCap is a project within ARM research in pursuit of such design based on seL4. Also contributing to this work has been Hisham Al-Matare of the University of Cambridge. By the time this recording airs, or soon after, IceCap will be open source. We'd love for anyone who's interested to reach out and get involved. While IceCap is a research effort that we hope to build out to the point of production readiness, it's not an ARM product, nor will it become one. IceCap is still a work in progress, but it's far enough along to have raised some interesting questions, one of which is the ultimate focus of this presentation. Again, here's our design in abstract. Let's zoom in a bit. seL4 runs as a hypervisor in exception level 2. That's the name for the hypervisor privilege level in the ARM architecture, analogous to ring -1 on x86. The host, in orange, now banished to exception level 1, runs as a Linux virtual machine. The host drives the hardware platform. Our goal is to enable the host to orchestrate guests and manage their resources at a high level without the privilege to view or interfere with their execution. The guests, in blue, run with confidentiality and integrity guarantees, protected from the host and the physical environment. Equally important is that they're sandboxed, because guests are mutually distrusting and also not trusted by the host. Green denotes our trusted computing base, that is, all software components trusted by guests to maintain the confidentiality and integrity guarantees they require. Remember, we're trying to minimize our TCB. Besides seL4 itself, there are some trusted platform components which run in user land. Some drivers, such as that for a timer, will have to be trusted, along with low-level resource management services such as the scheduler. We must trust the services responsible for guest lifecycle and attestation as well. Let's take a closer look at that. This slide outlines the flow for spawning a guest. The guest owner, somewhere out there, provides the initial state of the guest to the host. That will include an image and configuration. More on that in a bit. The host passes the initial state, along with resource parameters, to the trusted spawning service, which realizes that state. The trusted quoting service provides the guest with an authenticated record of its initial state, called a quote, along with some identifying information about the platform, which the guest can then use to prove to its owner that it's running as intended with the proper confidentiality and integrity guarantees. We call this remote attestation. The remote attestation part of this flow depends on a hardware root of trust and is not yet fully implemented. It's also out of scope for this presentation. The guest owner defines the initial state of the guest using an extended version of CapDL. CapDL stands for Capability Distribution Language. It's a language and set of tools for declaring, analyzing, and realizing the state of objects and distribution of capabilities in an seL4-based system. The variant of CapDL used at platform runtime by the guest owner allows for the referencing of external objects provided as part of the guest context. For example, that context may include some pages shared with the host and a timer server interface with a set of permissions for each of those objects. We've introduced an extern keyword for this purpose. Note that we haven't extended any of the CapDL verification tools yet. Even without the verification tools, CapDL allows for the guest owner to define a guest with great flexibility and allows the platform to implement high-level policies on guest resources and privilege. Let's consider how a guest owner might use such flexibility. What might a guest actually look like? A virtual machine with a virtual machine monitor would be a good place to start. Guests can also set up application-level enclaves that run just at exception level 0 rather than confidential virtual machines, but we won't focus on that case right now. In most virtualization platforms, the virtual machine monitor is part of the platform. In IceCap, it's part of the guest. The guest brings its own virtual machine monitor, and the virtual machine monitor is not part of the trusted computing base. A guest could even further partition their carve-out to include a protected execution environment for some particularly sensitive data that they'd like to protect from even their own virtual machines. Here's a closer look at one way a guest might choose to use their carve-out. In this case, the guest has declared a virtual machine and a virtual machine monitor using our variant of CapDL. We built a reference virtual machine monitor to demonstrate this use case. Our approach has been to achieve simplicity and performance by minimality. Our goal here is really just to port Linux to IceCap, minimizing emulation and context switches between the virtual machine and the virtual machine monitor. This approach is called paravirtualization. The VMM should really just be a shim between the Linux guest and the host. Towards that end, we've written the Linux kernel drivers so that most of the guest interfaces are attached directly to the virtual machine. In fact, the virtual machine monitor's only responsibilities are to inject interrupts and to emulate the generic interrupt controller. We're able to achieve this in less than 1,000 lines of Rust code. We have plans to reduce this even further, which I'll touch on in a bit. We're not yet far enough along to have rigorous benchmarks. However, we run sanity tests just to make sure we're on the right track. We've run iPerf on the host guest network on the Raspberry Pi 4 and observed about 92% of the throughput of Firecracker under those same conditions. Firecracker, the open source VMM from KVM by AWS, the open source VMM for KVM by AWS used by their Lambda service, serves as a good point of comparison because it follows similar design principles, namely minimalism. To be clear, I'm not making a scientific claim about the performance of IceCap. I'm sharing where we're at in our implementation so far. We've got plenty of optimization work left to do, especially in our Linux drivers. As mentioned before, tenants may choose to subdivide their carve-out to keep their own rich software away from the sensitive data. That's easy enough with CapDL. The IceCap seL4 userland is written almost entirely in Rust. Rust provides us with memory safety and the ability to write code at a high level of abstraction. We've also ported Mirage OS, the OCaml unikernel, to IceCap, which means that guests can be written as OCaml programs. As I mentioned before, by the time of this recording airs or soon after, IceCap will be open source. Now's the time to address an elephant in the room. seL4 has one big kernel lock, meaning that the kernel itself can only be running on one core at a time. There's good reasons for this decision, but it means that scaling an seL4-based system across loosely coupled cores is not straightforward. The questions are for what range of hardware platforms the big kernel lock affects performance and availability for IceCap, and whether clustering would allow us to break into that upper range. While the cloud may be out of reach, IceCap has been designed with the edge in mind rather than the cloud. We'll have to conduct experiments, but well-designed and well-behaved hosts and guests should not need a whole lot from the kernel, especially if they're using proper interrupt mitigation techniques, which they should be using anyway. The main issue we're concerned about is delays during interrupt handling for the host with malicious guests. However, we have ideas for a pair-virtualized interrupt controller to even further reduce VM exits during interrupt handling. Now it's time to address the confidentiality and integrity of guests in a broader context. We trust seL4 to handle isolation of the application on the application processor, but that's just part of the picture. What about the rest of the hardware platform? For one, the host controls devices with DMA. We could use an SMMU. That might allow us to deprivilege the host, but it doesn't properly address other aspects of our threat model, such as attackers with physical access. If we take a step back and abstract away some of the detail, we see that our requirements are actually quite simple. Because the host drives the hardware platform and sandbox guests just run on the application processor, we really just need one security boundary that extends out from the application processor and across the rest of the system. The ARMv8 security extensions, also known as TrustZone, are a perfect fit. That's what the remainder of this presentation is about. ARM TrustZone, also known as the ARMv8 security extensions, dates back to ARMv6 in 2004. It's quite a simple system primitive. Recall that's exactly what we're after. Here's a simplified view of a typical system without TrustZone. You've got your system components, such as the application processor and devices, and a single physical address space. It's hard to protect code running in the application processor because memory is exposed to devices with direct memory access or DMA. A system with TrustZone has its hardware resources partitioned between two security domains, the secure world and the non-secure world. The system has two distinct physical address spaces, secure and non-secure. The application processor and distinguished secure devices can access both, while normal non-secure devices can only access the non-secure physical address space. How the secure world is actually protected from the non-secure world and the outside world depends on the hardware platform. For example, memory in the secure physical address space might be backed by on-chip SRAM, or main memory encryption may also be used. Some platforms allow for dynamic partitioning of DRAM and devices between the two physical address spaces. That is, devices and regions of DRAM can be dynamically reassigned as secure or non-secure. ARM's IP solutions for these features are the TrustZone Protection Controller and the TrustZone Address Space Controller, respectively. From the point of view of the application processor, page table entries have an extra bit called the NS bit, stands for non-secure, which logically extends the physical address. For a particular page table entry, based on the value of that NS bit, a virtual address is mapped into either the secure or non-secure physical address space. TrustZone also adds a global bit called the NS bit to the processor state. This bit can only be touched in exception level 3, the highest exception level. When it's set, the processor is in the so-called non-secure state and can't access the secure physical address space at all. The NS bit allows for a coarse sort of context switch called a world switch between the so-called secure and normal worlds. Secure monitor firmware running in EL3 switches worlds by stashing some processor state and then flipping the NS bit. The normal world, which runs with the NS bit set, can't access the secure physical address space. The normal world hosts a rich execution environment, and the secure world hosts a trusted execution environment. Here's a closer look at how software is typically organized in the two-world model. ARM provides a reference monitor implementation called the ARM Trusted Firmware A. On the non-secure side runs your typical Linux and KVM. Opti is an open source so-called trusted operating system. It's a small operating system for running signed trusted applications. Trusted applications provide trusted services to the rich execution environment. For example, a trusted application could implement a firmware TPM or some user authentication components. The normal world calls a trusted service invoking a world switch by issuing a special instruction called SMC, which traps to the monitor. Note that while secure EL2 has been specified, no hardware platform is implemented yet. It's on its way though, more on that later. The coarseness of the context switch enabled by the NS processor state bit simplifies the secure monitor firmware, minimizing the attack surfaces of the attack surface of the trusted execution environment from the rich execution environment. So that's how software is typically organized across TrustZone. But as we all know, seL4 is not typical software. Let's take a step back to the overall system architecture of TrustZone. We've got this simple primitive that allows us to protect code running on the processor from the non-secure world and from the outside world. That's precisely what we need for IceCap. Once again, here is that typical two-world firmware design. The purpose of this design is to restrict the normal world software on the application processor to non-secure resources. Software level isolation between the secure and normal worlds is critical, so we settle for this coarse context switch, the world switch, to simplify our firmware. We can trust seL4 to handle this software level isolation on the application processor, eliminating the need for world switching using that global NS processor state bit. Specifically, we can leave the processor in the so-called secure state and position seL4 in secure EL2, where it will restrict normal world software to non-secure hardware resources using the NS bit in page tables alone. So we go from this to this. This is the straightforward division of trusted execution environment and rich execution environment that mirrors what the two-world model is capable of. Note that now the two worlds communicate using standard seL4 IPC. Here, you'll notice the first limitation of this approach, and that's that EL2 is occupied by seL4 and thus unavailable to the normal world. That is, no KVM in this setup. Another argument against this approach is that we lose out on the defense in depth provided by the global NS processor state bit. There's a debate to be had between that defense in depth versus the assurance provided by having the formally verified seL4 kernel as the most privileged software on the system. Other benefits of this seL4-based firmware design are that all less privileged components can be written and verified at a higher level of abstraction against the solid foundation seL4 provides and without performance overhead. Finally, as opposed to the rigid two-world model, seL4 enables us to isolate with more granularity, enabling for richer trust and isolation models. Instead of just that one isolation boundary, we get as many as we want. Now, we can introduce our guests, which run on secure resources, but are sandboxed with a high level of assurance by seL4. And we've circled back to our IceCap design. The host virtual machine runs on non-secure world hardware resources, whereas the rest of the system, that is our trusted computing base and sandbox guests, run on secure hardware resources. Now, with a more convincing story for the protection of guests from the host and from the outside world. To run full guests, which may be full virtual machines, on secure memory requires a hardware platform that supports memory encryption and dynamic partitioning of secure and non-secure memory. That's not so common today, but my colleagues in ARM research are hard at work towards changing that. Also, this design requires a hardware platform which implements secure EL2. Secure EL2 was introduced into version 8.4 of the ARM architecture back in 2017 as an optional feature. We expect the first hardware platforms implementing it to be available by early 2022. So far, I've described a TrustZone firmware design where seL4 in secure EL2 replaces the typical secure monitor in EL3. In particular, I've shown how that design works within IceCap. However, seL4 could fit nicely into other, more typical TrustZone firmware designs as well. Again, here's an example of a typical layout today, with opg as a trusted operating system. seL4 could run as a trusted operating system as well. Note that, in this case, and some others I'll show, seL4 isn't the most privileged software. The secure monitor, in this case the ARM trusted firmware, would have privilege over seL4. This complicates the meaning of the assurance you get from seL4's formal verification effort. Once secure EL2 is widespread, we'll start seeing virtualization in the secure world using what's called a secure partition manager. The Hafnium hypervisor will serve as the reference secure partition manager. seL4 could also serve as the secure partition manager. Now, just to place IceCap in context, here's what it looks like from this perspective. Again, all of IceCap runs in the so-called secure state, but at this point, the terminology breaks down a bit. You could also apply the seL4-based TrustZone firmware idea from IceCap to a more typical seL4-based system where seL4 runs in EL1, and there is no host operating system. TrustZone would allow for some components to make use of secure world hardware resources, allowing the whole system to operate under perhaps a stronger threat model. Of course, whether this would be useful really depends on the hardware platform and the application. On seL4 on AR64 today doesn't support TrustZone. Now I'll talk briefly about the extension that's required. This extension is AR64 specific and will be necessary to run seL4 in the secure world in any useful way. Today, untyped memory has a physical address. On AR64, physical addresses are actually limited to 48 bits, despite the fact that they're usually represented as by 64-bit integers. In order to run seL4 with TrustZone, untyped memory must span both the secure and non-secure physical address spaces. That's actually quite easy, as we can just augment our physical addresses with the NS bit. This works both at the API level and within the kernel itself. We don't need to touch the API, just the kernel's internal memory map. In the normal configuration of the kernel, untyped memory is either kernel memory, also known as general purpose memory, or device memory. Kernel memory can be used for anything. Device memory, however, can only be retyped into frames or more untyped. To support TrustZone, untyped gets a new dimension, secure or non-secure. Now, secure kernel memory is our general purpose memory. Secure and non-secure device memory are subject to the same restrictions as our familiar device memory. Non-secure kernel memory is subject to those same restrictions, except frames derived from non-secure kernel memory may be used as IPC buffers. Again, no API changes are required. We just need to sprinkle some checks across the kernel to maintain these invariants at untyped, retyped, and thread creation. For the non-hypervisor configuration, it really is that easy, just around 200 lines of code. However, we hit a bit of a snag for the hypervisor configuration. This isn't the right place to go into the nitty-gritty, but in AR64, stage 1 and stage 2 translation tables are actually distinct structures. seL4 on AR64, as implemented today, doesn't distinguish between the two. TrustZone is where that distinction comes into play, and that distinction would need to be reflected in the kernel, and possibly even in the API, if seL4 were to run as a secure world hypervisor. Note that we haven't addressed the verification of any of these TrustZone configurations for seL4. In fact, the existing AR64 code in seL4 is itself not yet verified. By the time this recording airs, I will have started a discussion in the seL4 discourse with the intent of working towards an RFC. We welcome your participation and feedback in the discussion around this proposal. Now that IceCap is open source, we'll be continuing our development in the open. We welcome contribution and involvement of any kind. Please feel free to reach out to me by email about anything I've touched on today. Thank you for your time.